So I hope, well, I don't know. The computer demo was just to kind of give a little bit more insight on confidence intervals, okay? And that's what we've got. And so what we're going to do here is we're going to create confidence intervals, but for a difference between means, between population means, okay? Well, and actually, just for reference, I will leave a confidence interval for a population mean, okay, based on one sample. And this is y bar plus or minus t star times s over the square root of n. What we're now going to do is we're going to do a confidence interval for a difference between population means based on two samples. And so what we have going on here is that I've got sample 1, and then I also have sample 2. And sample 1 comes from population 1. And then sample 2 comes from population 2. And the question is, so we observed sample 1 and we observed sample 2. Does this tell us something about population 1 and population 2? And specifically, does it tell us about the difference between population 1 and population 2? So population 1 has a mean, mu, and we're going to write mu sub 1 to indicate that it's the mean, or mu, for population 1. And population 2 has a mean mu2. And we want to know, based on what I observe on sample 1 and sample 2, what can I say about mu1 and mu2? Let's just separate that. So I see in sample 1 and sample 2 what can we say about mu1 and mu2? Well, at first glance, we might just say, well, let's just make a confidence interval for mu1 based on sample 1. And let's make a confidence interval for mu2 based on sample 2. Here, I'll let you guys write that. Okay, so we've got mu1 and mu2, and or sample 1 and sample 2. And what we can do is we can say, okay, well, let's make a confidence interval for mu1 based on sample 1. Let's make a confidence interval for mu2 based on sample 2. Okay, and let's say we did that. Okay, so we'll say attempt 1, which is to what can be said about mu1 and mu2. So let's say let's make confidence interval for mu1 and a confidence interval CI confidence interval for mu2. All right, and let's say the confidence interval for mu1 ended up being, so whatever this is, how many licks it takes to get to the center of a Tootsie Roll Pop. Let's say this one, we ended up being between 60 and 78. And then, so this is licks to the center of Tootsie Roll Pop. Okay, let's say we gathered more data, we were able to make a better confidence interval, more narrow. And let's say over here we came not to Tootsie Roll Pop, but I don't know, licks to, is there another lollipop? Center of Chupa Chups. That's a right lollipop brand, right?
Yep.
That's a good one. All right, and let's say this one goes from 76 to 89. All right. Does this mean it takes more licks to get to the center of a Chupa Chups than it takes to get to the center of a Tootsie Roll Pop? Yes or no? Could they have the same number of licks to the center? Yes, no? Okay. So what we're seeing is this goes from 60 to 78, and this goes from 69 to 89, okay? So it seems like, okay, there's like a little zone where it overlaps. Maybe this number is 77, and maybe this is 77. Maybe it's the same number of licks to the center of a Tootsie Roll Pop. Or is that silly to think that? Is it better to just say, well, the average over here is lower, and the average over here is higher, right? The center, because the mean, y bar serves as the center, right? So over here, the center is like 69 licks, and over here it's I don't know, 85 or whatever, 83 licks or something like that, something like that. Okay. So is it better to just say, oh, okay, well the centers are different, so they aren't the same, or there's a little bit of overlap, so they could be the same. Okay. Well, I will just tell you, this is not the correct way to approach the answer to this problem. Okay. So what we should do is we should look at the centers and compare them and say, okay, the centers are different, but just because there's some overlap doesn't mean that they could be the same, but also there's still a possibility that they could be the same. So we have to approach our answer in a different way, okay? And the problem with saying the mean could be 77 or 78 over here, and the mean could be 77 or 76 or something. To say that the problem with saying the mean could be 77 over here and the mean could be 77 over here is maybe a little bit too, quote, optimistic. Okay, you're hoping, basically what you're hoping is that on one hand, your sample was on the high end, the mean is 77, and the random sample that you observed was on the high end, where 77 is still a plausible value. Okay, and on the other hand, you're hoping that 77 is the mean, and your sample was on the low end, where 77 is still a plausible value. Okay, it's a little bit I would quote say too optimistic. That's not the statistically correct or technical term here, but it's like we're being a little bit too optimistic for it to be likely. Does that make sense? It's as if two sports teams were going to compete against each other, and one is clearly favored over the other. But on any, maybe you look at all of the data and you say, oh well, on the worst day of this sports team, they scored only this point, and on the best day of this sports team, they scored this many points. So maybe the underdog will win. Okay, it's very unlikely for that to be the case. So what we have to do is we have to come up with a way to create a standard error that accounts for both groups at the same time, rather than saying, oh, well, let's make standard error for here and standard error here for here, okay? So we have to make the standard error for a difference between means. Okay, so this is known as the standard error of y1 bar minus y2 bar. And it's just going to be an ugly formula that we're just going to have to deal with. Okay. That's the standard error for y1 bar minus y2 bar. Okay. It can be illustrated with the Pythagorean theorem. So just imagine on one leg of the triangle, you've got the standard error for sample 1, S1 over the square root of n1, or S over the square root of n, but for sample 1. And you got S over the square root of n for sample 2. And if you combine those, you get S1 squared over n1 plus S2 squared over n2. Okay? And this, things are what we would call orthogonal when they are independent, and this is basically what this is assuming here, okay? And we won't get into the technical or the reasons why, but when we're going to combine standard errors, okay, for a difference in means, this is how we do it. Okay, so this is going to be our standard error, and this is what we're going to use in our confidence interval. So let's make a confidence interval. Okay. So we're going to make a confidence interval for the difference y1 bar, or not y1 bar, difference between the mean of population 1 and the mean of population 2. Okay, so we're going to make a confidence interval for the difference between the mean of population 1 and the mean of population 2. Okay, so this is going to be a confidence interval for mu1 minus the quantity mu1 minus mu2. Alright. What is this mu1 minus mu2? Let's say we're going to make a confidence interval for the difference between the average height of men and the average height of women. Okay. What do you think mu1 minus mu2 possibly be? What would that? What's a reasonable number? Well, what does that number represent? It's if we took the height of the average man, Okay, how tall is the average man? And if we found the height of the average woman, how tall is the average woman? And what's the difference between their heights? So a reasonable number is something around 6 inches, something 5 to 7 inches, something around there. Okay, average height of a man in the United States around 5'10". Average height of a woman in the United States around 5'4". Okay, about 6 inches. Okay, so we have to keep that in mind. Okay, sometimes it's easy to just see all these symbols and forget what this confidence interval even represents. Okay, so I'm going to just put down maybe an example. Where can I fit an example? I'm going to have to erase some good stuff here. Okay. So here's an example. Okay, so population 1, heights of males in the U.S. and population 2, heights of females in the U.S. Okay, adult male, adult female. Okay. Okay, so mu1 is about 70 inches, and mu2 is about, we're just going to say let's say 64 inches. Okay, so the true value of mu1 minus mu2 is 6 inches. Okay, that would be the true value of this. Okay, just using the kind of the pseudo real numbers that I've made up. And so if we make a confidence interval, we're hoping the confidence interval contains this true value of 6 inches. Okay, so confidence interval comes from data, and we don't know if our data happen to select tall men or happen to select short men, and we don't know if our data happen to select tall women or happen to select short women, but we're hoping that our confidence interval will contain this true value of 6 inches. Okay, so we'll make a confidence interval based on our data, based on data that's collected. Okay, and we hope that the confidence interval contains the true value of 6 inches. Okay, meaning that the true difference between the mean height of men and the mean height of women is 6 inches, and we hope our confidence interval reflects that. All right, so if I'm going to make a confidence interval based on data I've collected, what do you think would serve as the best guess for the center? Or the best guess for what this mu1 minus mu2 would be? What would I put in the center of my interval? Not 67. Okay, because it's not the average. It's not the average height. It's the difference. Okay. So what we're looking for a confidence interval that's going to try to get this 6-inch difference here. Okay. So if I'm making a confidence interval based on the data, the best guess that I have for the true difference is going to just be the difference between my samples. This is my mean of sample 1, and this is my mean of sample 2. This is going to serve as my best guess for what mu1 minus mu2 is. Does that make sense? So let's say I didn't know that the average height of a man is 70 inches and the average height of a woman is 64 inches. Let's say I didn't know that. And let's say I picked 20 random men, and the average height of these 20 random men is 70.5 inches. And let's say I pick 20 random women, and the average height of these women is 63.8 inches. Okay? At this point, my best guess for the difference between the average height of men and the average height of women, based on my data, is just going to be, I don't remember what it said, 70.5 minus 63.8. Whatever sample averages I see, that's going to be my best guess, and that's going to serve as the center of our interval. And just like we did over here, I'm going to go up plus or minus some critical value, and we'll talk about t star in a moment here, times my standard error. Okay? What's the standard error in this case? It's that crazy ugly thing that we made, s1 squared over n1 plus s2 squared over n2. Okay. And okay, so how do we pick t star? So t star, again, depends on our confidence level. So that's the same as before. But our degrees of freedom is a complicated issue here, okay? The degrees of freedom for t star, when we're dealing with a difference in means, is actually, there's a complicated formula, and I don't want, it's not worth troubling you guys with it, okay? So either the degrees of freedom, so in your homework problems, the degrees of freedom will sometimes be given to you, okay? Other times, we're not going to bother with the complicated formula for degrees of freedom, but we're going to use an approximation, okay? Okay, and we're going to approximate this with n1 plus n2 minus 2. The truth is, the degrees of freedom is going to be something in between n1 minus 1 or n2 minus 1 and this number, okay? The truth is the degrees of freedom is going to be between within some number here, but we're just going to approximate it using n1 plus n2 minus 2. But in the book, it'll talk about, there's a complicated formula on page 206 for the true degrees of freedom, but we're not going to worry about that. We're just going to approximate it using this n1 plus n2 minus 2. And so, okay, so let's just try out an example here, okay? And I leave up, I guess, well, before we do the example, I leave this up to show that things are very similar, okay? This, at the center of our interval, is our best guess for whatever we're trying to estimate. So here, we're trying to estimate the population mean mu, and y bar serves as our best guess for the population mean mu. Here, we're trying to estimate mu1 minus mu2, and y1 bar minus y2 bar serves as our best guess. And then we go plus or minus some critical value t star multiplied by the standard error. And here the standard error is s over the square root of n, and here our standard error is just this mess. But the structure is very similar, okay? Okay, so let's try an example. Okay, so let's say we did sample 1 and sample 2. I'm sorry, let me just check things here. Okay, so, and the thing is that the samples don't have to be the same size. Okay, you can have different sample size. So let's just say we're dealing with the licks to the center of the Tootsie Roll Pop and licks to the center of Chupa Chups Lollipop. Okay? Sorry, let me just think. Okay, so see if, make a confidence interval for mu1, so 3 things here, and then make a confidence interval for mu2, and then make a confidence interval for mu1 minus mu2. I hope I picked good numbers here. I'm sorry. Oh, 95% confidence intervals for all of these. know some of you guys are still working. That's okay. But I have put the answers up on the board. Okay. And I think confidence interval for mu1 and mu2 should be straightforward. Just make sure you are using the correct values, right? So for mu2, you want to make sure your n2 is 11, your y bar is your 86, and your standard deviation that you're using is 10. Okay, so make sure that's correct. And these should be the intervals that you create, a 95% confidence interval. Okay, and here is so maybe I will go over just making confidence interval for mu1 and mu2. Okay. So at the center of the interval, we are going to place our best guess for the difference in the number of licks. Okay. So we do y1 bar minus y2 bar, and so I have 75 minus 86, and I get negative 11. I'm going to go plus or minus some value t star, okay? And so t star in this case, I'm going to have 95% confidence, and our degrees of freedom is going to be n1 plus n2 minus 2. So in this case, I got 10 plus 11 minus 2. I've got 19 degrees of freedom. So at 19 degrees of freedom and 95% confidence, the number I'm using is 2.093. And the standard error is the square root of s1 squared over n1 plus s2 squared over n2. So s1 is 8. 8 squared over 10 plus s2 squared over n2, 10 squared over 11. So I got negative 11 plus or minus 2.093, and then I do this part in my calculator, and I get the square root of 15.49, which is 3.936. Okay, multiply that by 2.093, and I get negative 11 plus or minus 8.24. Okay, so on one end, if I do negative 11 minus 8.24, I'm going to get negative 19.24. And on the upper end, if I do negative 11 plus 8.24, I get negative 2.76. So this is my 95% confidence interval. What does this confidence interval mean? So, I mean, just for simplicity's sake, let's just say it's negative 3 to negative 19. Okay. Technically, it's this number, but let's just round to minus 3 to minus 19. What does that mean? If I want to make a statement, I am 95% confident that what is between negative 3 and negative 19? Think of what? So over here, the confidence intervals make sense, I think, right? I'm 95% confident that the number of licks it takes to get to the center of a Tootsie Roll Pop is between 69.28 and 80.72. So basically, I'm 95% confident that the number of licks it takes to get to the center of a Tootsie Roll Pop is between 69 and 81. And over here, I'm 95% confident that the number of licks it takes to get to the center of Chupa Chups is between 79 and 93. Okay, if that's okay with everyone? And here we see there's overlap, right? This one goes up to 80.7, and this goes down to 79.2, there, 79.3. So there's a little bit overlap. But can we say that they have the same number that it takes about the same number of licks to get to the center? Well, when we make a confidence interval for that, what we get over here is minus 3 to minus 19. So this is the correct interpretation here. I would say I am 95, so yeah, just listen for now. I am 95% confident that the number of licks it takes to get to the center of a Tootsie Roll Pop is between 3 and 19 licks less than it takes to get to the center of a Chupa Chups lollipop. Okay? I'm 95% confident that the number of licks it takes to get to the center of the Tootsie Roll Pop is between 3 and 19 licks less than the number it takes to get to the center of Chupa Chups. We'll write that down. Tootsie Roll Pop is between 3 and 19 licks fewer or less than the, I should say that the average, or mean, than the mean number of licks to the center of Chupa Chups lollipop. Okay, so when we compare the two brands of lollipops, do we have evidence that it takes one lollipop fewer licks to the center than the other? Yes, okay. We're 95% confident that the Tootsie Roll Pop, the number of licks to get to the center of the Tootsie Roll Pop is between 3 and 19 licks fewer or lower than the number of licks it takes to get to the center of a Chupa Chups lollipop. So that provides evidence that the number of licks it takes to get to the center of a Tootsie Roll Pop is less than the number of licks it takes to get to the center of a Chupa Chups lollipop. Okay? So we have to use a confidence interval for the difference in order for us to make a statement about the difference. We cannot just take confidence interval from mu1, confidence interval from mu2 and see if there's overlap or not. That's not going to work. Because here we see overlap, but that doesn't mean there's not a difference. We do have evidence of a difference. We do have evidence of a difference. Yes?
So if the confidence interval for the difference between mu1 and mu2 contains 0, does that mean you can't say?
Yes, that's exactly the next point I'm going to say. So the reason why we can say there's evidence of a difference is because it goes from -3 to -19. Okay, round it off. If the confidence interval for the difference contains 0, let's say it went from -19 to 5, then we cannot say that there's a difference, because 0 is a plausible number for the difference between the means. Okay? But here, 0 is not a plausible number for the difference between means, so we have evidence that there is a difference. So that's a very important thing to make note of. So if our confidence interval for mu1 minus mu2 contains 0, then 0 is a plausible value for the difference mu1 minus mu2. do not have evidence that there is a difference between means. On the other hand, if our confidence interval does not contain 0, meaning 0 is not between the ends of the confidence interval, okay? So basically, if the confidence interval is entirely negative or entirely positive, then we do have evidence of a difference. Definitely see a question regarding a confidence interval for the difference between means on the midterm next week. So please make sure you understand this. And I will ask, does this provide evidence of a difference between means? And you have to recognize whether. So in this case, our interval does not contain 0. It goes from -3 to -19, so it's entirely negative. So 0 is not in between -3 and -19. So that means we do have evidence that there is a difference between the number of licks to the center of one lollipop brand versus the other lollipop brand. Okay, and that's the only valid way. Well, maybe not the only one valid way, but if we're going to use confidence intervals, that's the only valid way to compare means. Okay, it's perfectly valid to make confidence intervals for one mean and confidence intervals for another mean, but it's not valid to compare confidence intervals and say there's overlap or there's not overlap. That's not okay. To just say I'm 95% confident that the number of licks next to the center of a Tootsie Roll Pop is between 69 and 80.72, perfectly fine. And to say you're 95% confident about this one, also fine. But you cannot compare those confidence intervals directly. You have to create a confidence interval for the difference, which takes into account the different standard error, okay, or the combined standard. Are there any questions on this? Okay, if that's it, we will finish there. And you guys have some homework. The homework this week is pretty light, and that's to give you some time to study for the midterm. So good luck on your studies. We'll see you guys next week, next Thursday, for the midterm exam.